Okay. Good afternoon. Thank you, everybody, for showing up. This is, of course, our weekly seminar, and it's a pleasure to have here Dr. Perlovsky, who's a scholar at Harvard, as well as a principal research scientist at the Hanscom Air Force Labs, and he's also the technical advisor there. Professor Perlovsky has he's actually been quite a bit around, and he was at New York University and Novosibirsk University prior to becoming the chief scientist at Nichols Research, and following that he started his career at the Air Force Research Lab. He's been extremely prolific. He has 2 books, 10 book chapters on neural networks, and he's mainly interested in the mind and the brain in general, and he's the editor-in-chief for Physics of Life Reviews. He's received numerous awards, one of them being the highest award at the Air Force Research. It's called the McLucas Award. It's a pleasure to have you here. Thank you for coming to share with us some of your work on culture and language and all that.
Thank you for generous introduction. Do I need a microphone or everybody?
Got it.
Oh, okay. Yeah. So where do I clip here?
Yes.
Or you have?
That's a good question. Let me show you very quickly, so you can.
I can just
move up.
Okay.
And down.
Excellent.
This way. You can actually write.
Okay. That's too complicated. I wouldn't.
And then you can put down and then. Erase.
Okay. Great. So I'll be talking about language, cognition, and cultural evolution. How much time do I have?
You have 15 minutes.
Okay. I have 36 slides. It's a little bit dense, but it's good enough. So let me first, because I might not go with equal density on every of these topics, so let me first tell you what I'm going to tell you about today. I'll describe mechanisms of cognition. I explain why specifically it was difficult to do it mathematically for the last 50 years. There was complexity of computation or of learning or of structures or of whichever people were trying to do for the last 50 years. And there are many different things. There was issue of complexity, which was more than was capable to accomplish in real time. And I explained that it was related to logic. Oops, I'm sorry. That it was related to logic. And to actually the fundamental difficulty of classical logic proved by Gödel in 1937. So the reasons that our algorithms didn't work for 50 years had good reasons. There was deep reasons behind it. Then I'll go to how, because logic doesn't work, I'll go and I'll tell you a few words about how the mind works. And there is such thing as mind that I called knowledge instinct. And biologists were studying it for a long time and called it a different way, but they didn't know that it is very important. Mathematics shows that it is fundamental to our mind. And I'll tell about some mathematical techniques that actually implement this thing mathematically. And they have their corresponding mechanisms in the brain. And so we now know how to explain a lot of things about mind. Of course, not everything. You know, if you have your own just personal ideas in your mind, which could be crazy, I'm not sure that I can describe them mathematically. But some more simple thing, how the mind, recognize objects, come up with ideas. We probably have some ideas about that. And so I'll go from objects to higher cognitive functions. And then most important for me now is things such as how cognition and language are integrated. And I am probably the only, well, no, I shouldn't say that. There's a whole direction of people who want to know how to do this, but they are of psychological origins. Mathematicians have no idea how cognition and language is integrated, didn't even ask this question previously, and people who study the mind don't know where it happens. So that's really a big mystery, but mathematically we can say and restrict how it could happen in many ways, and so we have a good idea about that. And then I'll show that it is actually possible to come up with evolutionary cultural models which are based on the basic mechanisms of the working of the mind. Whereas what most of people today, of course, predicting cultures is so important today. Clearly, we don't understand what's going on in Iraq. They clearly don't understand what we are doing there. There is big disconnection between the various parts of the world. People don't trust each other, and so it is important to have scientific approach toward understanding what's going on. And there is a lot of effort to do cultural modeling, but those modelings are based on material, so to speak, factors such as demographics, economics, environment. But what I'm saying is that probably most of what's going on in the world is coming from people's minds, or at least is related to what's coming in people's mind. Who comes from what? It's a big question. I think maybe our mind are coming to some extent from culture, but of course we affect the culture. So it is an important thing to be able to do engineeringly, not just psychologically say, oh, I understand how things happen. Can you go to people who make political decisions and tell them, here is an engineering tool that will help you? So that's kind of direction in which I would like to go. And just, there's a lot of things. Well, I'll just scratch surface. In all of this area, I just scratch surface. If you would like to do things in this area in future, there is a lot of questions that I can tell you right away where you can put your mind to. So first, why it was difficult to make cognitive perceptual algorithms in the past. Why our computers don't serve us coffee in the bed. As the joke goes, if you want coffee in the bed, you first to get up, make coffee, serve it in the bed, then lay down and drink it. But you can have robots do it for you. And there are computational reasons for why it was, it was so difficult to do. And here is the main fundamental reason. No matter what we did, when you want to go from pixels to objects to scenes to understanding what's going on, there is combinatorial complexity happens, because in order to get from pixels to objects, you need to decide which pixels belong to which objects as a part of the scene. You go from, etc. So you need to do this, you need to select subsets among a significant number of things. And if you remember your math, whichever, or 1 or maybe or 2, when you number of subsets is very, very large. Namely, it is combinatorially large. And even if you look at, did I do the single already?
Yeah, you have to put down the pen. Put it back down. Put down the pen.
Okay.
No, in its place, right? Then you can erase.
Oh, okay. Thank you. I'll do with some other pens then in the future. This would be safer. Okay. If you think about very modest number of elements in your systems that you try to understand, and you have to look at combinations of those elements. Combinations of 100 is 100 power 100, and it is literally larger than all our entire universe in all of its time of existence. So clearly the mind does not sort through combinations. And, but all our previous algorithms did. So let me explain why did. Now, very, very fast. I'll go through, well, as you see, I'm quite obnoxious guy. Now, in 2 minutes, I will summarize what was going on in all of the computational intelligence and artificial intelligence in the last 50 or 60 years. When we were trying to do statistical pattern recognition and early neural networks, 50s and 60s, we faced learning requirements. That is, it looks like these algorithms can learn anything on their own. Only you need to provide enough of training examples. You need to provide examples that this is a pen, but also when it's held by this hand, it is another example. And with this guy, and with all of the things around, you need to teach it on all combinations of all things that you will be able, this neural network, to recognize. I assume it will work, but still number of combinations of your training examples make it impossible. Then people say, okay, learning is difficult, but rule systems, we know how to do it. We will formulate rules. After all, Minsky said, Newton invented physical laws. We just read about them in the book. Let's get away from the idea that now computers will invent things. Let them just use the knowledge that we have. So let's put all the rules together, put them in a computer, and have computers, just do things the way just we're supposed to do without learning. And it worked all right. And by the way, it is still working. all over the place and all the factories. And whenever we have artificial intelligence working, it is mostly because of this idea. But as soon as things start changing, you need to adapt and modify what happened, and these rules start growing into trees of rules, and they become combinatorially complex in terms of how do you combine various rules with each other. And then in the 80s, both in, now Kosminski is a guy who worked in artificial intelligence, and Chomsky is a guy who started contemporary directions in linguistics, and they faced both same difficulties. And in the 1980s, both of them actually, not both, the whole areas of science switched to another paradigm, from rule systems to model systems. They say, let's have models that could adapt to various situations, but still, whichever we know, we will put inside of this model. Say, chair, it has something like this, you can sit in it, has four legs, but exact positions, color, angle at which you look could be adaptive given to given situations. And that's a great idea, but it still doesn't work, because you need to decide, like when I look at this thing, this object in front of me, I need to decide that these pixels in my eye correspond to chair behind it, which I actually don't see, but these pixels correspond to this table. So I need to make sure which combinations of pixels in my past memories make sense. And this is combinatorially complex. And today people try to do semantic web, ontologies, but all of these things today are still rules. When in the future people will try to do them adaptive, they will face all, and by the way, people already start doing them adaptive, and they already don't work. So if you go in a company who's doing semantic web and they have difficulties, you can tell them right away why do they have these difficulties if they don't know themselves. So it turned out that combinatorial complexity is related to logic. It is, I wouldn't go through all the details, but I'll just tell you that if you look at how Gödel proved that logic doesn't work, so to speak, without a lot of mathematical niceties. Logic is not as logical as people used to think it should be. And it was, a lot of people think that it is the most important mathematical result of the 20th century. And if you look at how he proved it, you will see that if you have finite systems, not infinite systems such as arithmetic or logic, but finite systems such as computer, for example, then you see that Gödel proof becomes combinatorial complexity. So it is a very fundamental reason that all our algorithms of the past didn't work. The people, I am not the first one who realized it. Zade came up with fuzzy logic, especially to avoiding this kind of difficulties. But in fuzzy logic, it is engineer who should select the level of fuzziness. But if you think about such a complicated thing as brain, there's thousands, millions of processes going on at the same time in different, not asynchronous in various parts of the brain, solving different problems, and all of them have to select their own level of fuzziness, which changes all over the place. So if you try to put a fuzzy logic system that will select their levels of fuzziness adaptively, according to situations, you'll get to combinatorial complexity. So logic, the bottom line of this chart is that logic pervades everything we were trying to do before, and therefore, and the neural network was because of training, and fuzzy logic because of degree of fuzziness. So logic is all over the place, and we didn't know how to get around it. And that's what I will tell you today, that there is a new mathematical trick, which some people doubt that it is logic, but other people actually right now today writing papers saying that yes, it is logic, and which gets away the difficulty of standard Aristotelian logic or formal logic faces. And this new thing I call dynamic logic. Dynamic for the following reason, you will see now, because it is a process. It is not just statement. It is a process. It is a process from vague to crisp. So if you want to say things in short phrases, the right phrases going from vague to crisp. So initial vague statement or concepts or plan or model in your mind, in your thinking process, is becoming more concrete and concrete and concrete until it really matches all the requirements that you are trying to take into account and become really crisp plan or crisp model of something. So the idea is simple. The question is only how to do it mathematically. Mathematically, it is based on similarity between models and signals. So indeed you have, and we have models, everyone have models in our mind. We understand the world in terms of models. And these models, again, as I said, go from vague to crisp. And if you want, let's make an experiment. It will take 15 seconds to prove that actually the mind works according to dynamic logic. Look at any object in front of you that you know very well, computer or chair or this desk or myself, whichever. Then close your eyes and please actually do it just to convince yourself that it is so, just for 10 seconds, and try to imagine the object that was in front of your eyes just a second ago. Clearly, your imagination is not as exact, not as clear, not as clear-cut, not as crisp as when you actually look at the object. What does it mean? Actually, it means that your representations in your mind, and today we know it exactly, that what you see with closed eyes is your representations existing in your mind. And they are not as crisp as when you see at actual objects. They are vague. And actually, it was recently confirmed. Yeah, by the way, that is the reason mathematically it avoids combinatorial complexity and results in fast algorithms. But also, it was recently confirmed in medical neuroimaging that actually that's what goes on in our mind. That when we perceive something, our perception starts unconsciously from vague representations. And then these vague representations, when you kind of look at particular objects, these vague representations jump and grab this object, and then you understand what you are looking at. Okay, so what I told you is that cognition is a complicated thing, and logic did not describe it. But let us look at how the mind, well, mind still works. We still see objects, we understand them. So let us see how it happened and what we can say about mind and what kind of neural or modeling mathematical techniques can describe it. Actually, we can say a lot about things. Here is how the mind works in terms of like describing it in words. Of course, if anybody will tell me, well, if I will tell to anybody that, look, here's how your mind works, people will laugh at me. They say, oh, my mind is so complicated, I can't understand myself what it is doing. And you're telling me that these 3 lines, or 5 lines describe what my mind is doing. And I'll feel embarrassed because indeed, we are complicated beings. Nevertheless, let us see how far we can get toward understanding the mind. Mind works with concepts, and concepts mathematically, so we understand world in terms of concepts, and mathematically very easy to describe. And concept is, say objects are concepts, or situations are concepts, or even abstract things are concepts. That's just there's mechanism of concepts. And mathematically it is easy to describe. It is mathematical models of whichever we want to understand, and we match these models in our mind to whichever is around in the world. And if we succeed in matching, we understand what's going on. Okay. Concept is relatively late in evolution, in biological evolution. Of course, simple animals don't necessarily have concepts, but they have instincts. Instincts are, both of these things, of course, are mechanisms of survival. But instincts are much simpler and much older mechanism of survival. Instinct has really like wired in instructions of what to do in various situations. Like, if you can imagine what are instincts for, say, a worm who goes where it maybe a dumper and, not dry and maybe warm, not very cold. He's doing it instinctually. His instincts directly, or she's or whichever, directly wired to the muscles, and eat, you probably cannot say he or she, just eat. It is a simple mechanism that goes where it feels better. Now, but in complicated animals like dogs or all higher animals and human beings, these two things are connected. Clearly, concepts came up in evolution not just for their own enjoyment of life, but because more complicated animals could better understand the world and better survive instinctually if we have concepts. Because instincts in complicated situations could come to contradicting each other. So you need to understand what's going on in order to make decisions. And of course, every one of us faced it a lot of time in our life. Do you go to university where whichever you paid full tuition, or do you go to university maybe which is more selective but wouldn't give you those kind of things come up all the time. And in order to make a decision, you need to have conceptual understanding. But what is connection between these two things? Connection is emotional. We usually don't necessarily understand it that way, but that's what people today know, that emotions connect instinctual parts in our brain, somewhere there, with conceptual parts somewhere here, and they connect them in the following way, that while we are understanding certain things, before even we understood them, like before we understood what is in front of us, this mechanism of emotions work in the following way, that emotion, so to speak, pain, so to speak, or color, objects or concepts or ideas that we might entertain with usefulness of these ideas for particular instinct. For example, if my leg hurts and I'm tired, I start automatically looking for where can I sit. And I noticed only chairs or other objects on which may be not very convenient, but at least I can sit. And this is done emotionally, because emotions connects instinctual, it is different kind of signals from instincts or from concepts, but they connect these two, and they say that this particular object is good for satisfying your instinctual need that you have right now. That's the role of emotions. So you see, we understand already a lot about how the mind works. The problem only how to make it all mathematically. And then, of course, engineering, and can have a robot who will serve us coffee. Still not a lot of problems to solve. And of course, there is behavior, but I will not be talking too much about behavior today. And what is important is that there is hierarchy. All of these things are organized in our brain in the hierarchy. At the top, at the bottom of hierarchy, we understand some features, and then objects, and then situations. Like, for example, I understand this scene as composed of everything that is here. And then I can think about general things such as law and friendship and love, whichever. And I'll get to it later. So this hierarchy is what really makes us complicated beings. So we are not exhausted, so to speak, but these few lines. But I'll tell even more about it, why this is so much more complicated than these few lines just appear. So first of all, let me emphasize one strange thing, that when people talk about instinct, they say, of course, eating and avoiding danger and sex are our most important instincts. Procreation, of course, without it we wouldn't survive. But it turned out that it is all true for worms, but when we get to higher animals and human beings, another instinct is even more important. And this is instinct, I call it knowledge instinct. And biologists were talking about it since 1960s, but they didn't appreciate how important it is. Only mathematics explain how important, because models or concepts in terms of which we understand everything around us always have to be adapted to what is in front of your eyes in this particular moment. So you see, this is, on one hand, it is obvious, but on another hand, that means that you have to adapt, or you have to learn all the time. Otherwise, you wouldn't even see what's going on in front of your eyes. And so this is the most important instinct that make, you want to do it, or you don't want to do it, or you need something, or you don't need anything. At least you always need to understand. So we have this instinct that drives us to do that. And mathematically, it is easily to describe. There should be some similarity between models and objects in the world, and we maximize the similarity. So that is how you mathematically describe knowledge. So you see, I already explained to you half of what our mind is doing, or more than half, and I didn't write any equations. So you see, equations are always secondary. I'll, of course, show you equations later. You can go on web. If you really want to know, you type Perlovsky, and you'll see more equations than you want. But that is the main idea. The main thing is to understand what's going on in our mind. And there are, as I said, every instinct goes with its own emotions. Like there are emotions related to if my leg hurt, I have emotions. If I'm hungry, I have another emotions, and I have many emotions for many different reasons. But there are different emotions which are only related to what's going on in my brain. I want to understand. If you don't understand what's going on around, it's really a scary thing. For example, thriller movies are based on exactly on this thing. They show you something that contradicts your understanding of the world. And this is very scary. We really, like if you cannot bite apple, you cannot open the door, you cannot get into room, out from room, it is scary. And that's what thrillers exploit all the time. So it is really very, very important, as I say, the most important things. And we feel it like this. We feel it, let me put it in a nice, so to speak, half-scientific way. We feel it as a harmony or disharmony between our knowledge and what's going on in the world. So our knowledge have to correspond to what's around us. And this is very important to us. Here's a description, mathematical description of this system. And of course, I simplified the whole thing. I described just saying there's bottom-up signals that coming from the sensors up to the mind. And there are top-down concept models which send signals. They are located here. People say in orbitofrontal cortex, which is here. And they send signals from top of the mind down so that they meet in the visual cortex. And if models correspond to signals from the eyes, then we recognize things. So nothing, well, I don't know, maybe I should say nothing new. For engineers, it is not new, but for medical people and psychologists, and it is a very, very new thing. Only very recently they were able to actually prove that that's actually what's going on in the mind. There is a little bit more equations because we need because knowledge instinct maximizes similarity between signals and models, top-down and bottom-up signals, and this is how it's written. It is a product of a sum and product of all the signals and sum over all the models. And you see, if you take sum, substitute inside of product and multiply everything, there would be number of models power number of data points. So this is where combinatorial complexity is coming from. That's why anyway people were trying to solve problems, they always were solving this problem because you cannot avoid. That is a problem you have to solve. And it leads to combinatorial complexity if people do it, if people try to consider every item separately, as that's what people actually were trying to do. And here's what dynamic logic is doing. It is a very simple idea. It says, let's not multiply all the things, but maximize the whole expression. And it is doing it in the following way. Let's form first these association variables. And if you know theory of probability, you could recognize that it is what's called inverse or a posteriori based probabilities. But if you don't know that, even better, don't call them that way. It's just variables. And you see they are normalized in a nice way, like probabilities are normalized, because you have this thing in the at the top and sum of all of them at the bottom. So you have something that is normalized between 0 and 1. It has to be between 0 and 1. And that's convenient to have something like probability. And then you have something that looks very much like a gradient ascent. You see, this is, okay, now, let me make a step back. To write this thing, I need to know what are the parameters and the shapes of the model. So let's assume somehow models came from somewhere. I only need to know their parameters. And I don't know parameters, of course. So I start with wrong value of parameters. Everything is wrong. But I have this equation that will improve parameter values, like gradient. Gradient is good, is much better than sorts, because if you sort to select the best thing, you have to sort through all combinations, and there is combinatorially large number of combinations. But if you just go up the hill to the maximum, to the top, to find maximum, there is no combinatorial complexity, so you do 10 steps or 100 steps or 1,000 steps, but computers can do it fast, and our brain is doing it very well. So you can improve, even start with entirely wrong values of parameters, and then you can improve it. And if you forget about this thing, this looks like gradient ascent. But the difficulty is, of course, that you have many models. So you need to decide which part of your signal you can use to improve which model. And that's what is done with these variables, which are staying here. And that is the only thing that is different from standard gradient ascent. So you can say, you can look at it as a gradient ascent for improvement of parameters. And you go through this iteratively, because, of course, you start wrong. So what you do first time with first step. Now, of course, this is what you have on the previous iteration you put here, and here is the next iteration. Of course, they're not equal to each other. Well, like in a computer, you put the same variable on each side of equations, and they really mean different things. So, so this is how it works, and there is a nice theorem that actually it converges. And it converges in an interesting way. It converges in such a way that the likelihood, the similarity, which I have shown you previously, always increases at every step. And that is a nice thing to know, and it has a good psychological interpretation that aesthetic emotion that is associated with knowledge instinct is always positive. So this algorithm enjoys learning. And it explains why you, instead of taking drugs or alcohol or watch TV, sit here and enjoy this very boring stuff because we enjoy learning. Okay, so let me show you an application example. I have how many? Another maybe 15 minutes? Yeah. Okay. There are many applications, and I would go even financial. I even make some money in the financial market. I even predicted 9/11 a week in advance, and then helped SEC to look for these guys, because Al Qaeda actually was trading probably trillions of dollars on a week before. And so my system were able to catch ripples of these things and tell them where to look for these bad guys. Maybe they found them, I don't know. They didn't tell me. Well, this guy is, but he was not trading, I'm sure. He was not sitting behind computers trading things, but there were brokers who were trading, and I would be surprised if they didn't identify them. Maybe they did something to them, or maybe they, I don't know, asked some friends to take care of them, I don't know. So we did a lot of things. We even are doing ontologies for semantic web. Okay, but it takes too much time to tell to everything, so let me show you one example. So here is the signal, and you see there is a lot of noise, and you don't see anything. But because the thing is simulated, so this is random noise, but we know that there are targets that looks like this. And it is important for specific applications, for specific people who want to be able to find this kind of patterns. But you see, even with your eyes, you cannot see it. And if you cannot see it with your eyes, it is hopeless that computers will be able to find it. Nevertheless, as you see, as you will see now, computers will find it. So this is, I told you, dynamic logic start with knowing nothing. So it is a big fuzzy blob. And this is how our mind starts understanding things if you don't know what to expect. So you have a big fuzzy blob. I'm sure computer movie wouldn't run, because probably, it is not connected. So, okay, this is how this movie looks like. This is what I already have shown you, and this is a big blob. And then it runs, actually, it does 22 iterations. And you see, it reduces uncertainty. And it decides, here it probably decides that there is more than one object, maybe two, because you see it is not circular. And here it decided that there are 3 objects, and then it stays with 3 objects. And then up to here, it thought that objects are circular. and it doesn't know more than circular and parabolic objects. And then it decides that objects are parabolic, and then it fits them exactly, or nearly exactly. So you see, it works, and it is a big deal, and I get awards for this kind of thing, because it is 100 times, in terms of signal-to-clutter ratio, in this example, it is 100 times improvement of what people were able to do before.
So what's your prior here?
The prior is that this is a signal. My prior, I knew that there are parabolic objects, maybe circular objects, and maybe linear objects. So that's the whole knowledge that I had. Of course, it's very much simplified. There's a lot of other objects in real life. But I needed to start from somewhere, and because I wanted to get, award rather than solve all possible problems. So, so I advise you to do same thing before your dissertation. Solve simple problems first. Okay. And you see, in terms of combinatorial complexity of this thing, it is absolutely unsolvable. It will stand to the power of 5,000. It is more than all the universes that ever could exist in whichever is the place where many universes exist. Certainly more than a single universe, and more than everything that can happen to you. And in terms of, but with dynamic logic, it is very reasonable performance. We can do it, in 15 seconds, or maybe in 10 seconds, or maybe in 1 second on PC. And improvement in terms of signal-to-clutter ratio is 100 times. So that was great success, and we have a lot of examples like that now. But still, there are zillions of different problems. We don't know how to generate models automatically, so always it requires some ingenuity to make it work right. So let's go to higher cognitive functions. What I did, I've shown you just simple objects, how to recognize simple. But now let's look at higher cognitive functions. So this is a simple, simplified architecture for a single layer for objects. But to get to higher cognitive functions, you have to have many of these. And at the bottom, you have objects. And then you have situations. And then you have meanings. And of course, I am simplifying because there is much more than the 3 layers or 4 layers. There are probably hundreds of these layers. Yeah, like, at the very top, there's probably one big, vague model of everything. Because we want to understand not only every individual object by itself, but what is the meaning of this object as a part of situation, as a part of just general ideas. And finally, we want to understand what is our role in the universe and why we are living. And this is probably at the top. And so if people talk about religion, there is very good mathematical reason to say that, of course, religion is very important. It is how you make this single model that understand everything. Because we feel it as a meaning of our life. So, of course, we know nothing about it. It is completely vague, completely non-understandable. And so if people want to call it religion, it is quite a reasonable way of doing it. Of course, if people start killing each other because of different understandings, you can say, well, they better go and study math. Maybe they'll better understand what's going on. For example, we can explain what is beauty. Beauty was never explained. What really is beautiful. When you look at something and it is beautiful, why? Why certain things are beautiful and rather than not? And today most people think that it is related to sex, but actually beauty is not related to sex. Sex, of course, is related to beauty, because sex related is to everything we know how to do. But beauty, ability to perceive and make beauty is a specific ability, and it is the highest aesthetic emotion. Aesthetic meaning emotion related to improving of the model. So if you see object that kind of, it cannot really improve your understanding of your meaning of life, because you cannot understand meaning of your life. It is vague and will never become exactly crisp. But even if it reminds you that, well, maybe there is something like this, then you feel, wow, that's great. So it is not that you go to a gallery and you look at a particular painting, oh, it is Leonardo da Vinci, how beautiful it is. No, nothing will jump out of this Leonardo da Vinci on you, and maybe there is not big, of course you look at it as beautiful, but not everybody will necessarily get excited about Leonardo da Vinci. But it doesn't matter where it happened and what's the reason how it happened. But if you feel, wow, it really means something to me, that's what's beautiful. And it doesn't matter where it happened, in the field or in the factory or in the university or, when you're with a girl somewhere. Of course, with girls, then it's difficult to make difference because sex is also very powerful and make us, or girls with men, you can, of course, get very excited about what's going on. And it could be, beauty probably plays a role there because sex makes use of all of our abilities. So let's see how language and cognition are integrated. And even so, I say it is so difficult and nobody understands, but I'll explain it in 3 minutes because we don't know much about it. Chomsky, when he started, he thought that language is separate from cognition. And today we know, of course, it is wrong. He has reasons to do that. I shouldn't blame him. I think he's smart, very smart guy. Then 20 years later, there were guys who called themselves cognitivists, and they still exist, and some of them are very smart. And they, of course, not. Of course, language and cognition go together. Obviously, it is almost obvious because we think in terms of language. If you cannot try even to think without language because language is there. The only reason we can think about abstract things is by using language. And then later, another 10, 20 years later, there were guys appear who call themselves cognitivists. They say, when we think about how language works, we have to take into account the fact that language has to be transitioned from generation to generation. There is no way that your child will hear all possible combinations of words. The language should be structured in such a way that even hearing a very small sample, he will learn the entire language. And so these people call themselves cognitivists. And actually, this neural modeling field dynamic logic that I briefly have shown you previously was extended to language and can generate this kind of interaction between them. And then I'll go to how they co-evolve, how language evolution co-evolve in cultural evolution. Okay, here are the most important equations in terms of how language and cognition comes together. Every model that I say we use to understand the world has 2 parts. It has cognitive part, that is an object, and it has language part, that is sound that goes with this object. And what is important is that probably we are born, now I'm entirely just hypothesizing because nobody knows about what I'm saying for sure. But that's the only way that mathematically you can describe it. Or at least I understand how to describe it. We are born with this thing going pairwise. There are placeholders. Of course, when a baby is born, these are just vague placeholders of how cognitive and language things will come together. And that's what makes us different from animals. A dog, you say shoes, and dog will bring you shoes. But dog, because dog just hears shoes as a separate object, and it knows how to associate it with shoes near your, in your bedroom, and will bring it to you. But dog does not have the thing, hardwired as we have. Therefore, when later you hear something about love or about religion or about law, whichever, you read books and you start looking. Now, you fill in this thing with specific knowledge, but then you start looking. The knowledge instinct drives you to find what in the world corresponds to it. And that's how we understand, abstract things. So these 2 things work together, and one can help another in how it proceeds. Okay, so we have not a single hierarchy, but we have 2 hierarchies, the language and cognition. And you see, only at the very bottom, cognition directly is grounded in objects you see in front of you. But at the top, when you talk about abstract things, you cannot see them. We only know them from language. And that proves that, of course, that's the only way how it could be. Because language we know since 5 years old, we already understand everything. And then we start looking, where are those things that correspond to what we hear from our peers and read in the books and hear from our parents. Do I have how many? 5 minutes?
Yeah.
Okay. Yeah, I'll try to finish. So evolution of the mind and cultures. How the thing evolved together. Okay. The knowledge instinct has two parts. It has differentiation, which tries to understand at every level. You try to understand in more and more details what's going on, how many objects you can see around. But also there is a synthesis, because at the top you have a model that tries to understand the whole thing together. So the same mechanism drives both, just differentiating, creating more and more and more detailed models, but also creating models that could combine this differentiated knowledge in a single whole. And we need both of these things to survive. That's enough. I wouldn't say more because there is not enough time for this. I'll just model this thing. I'll just say how they're related to language. Conceptual content in different cultures could be exchanged. What I say in English, I can say in any other language, more or less, so that it will mean the same thing. Like fax. We invented fax, whichever. Say in US, I'm not sure. But then fax went around the entire world, people understand what we're talking about. But emotional content of culture cannot be exchanged between cultures. Emotional content resides in grammar, which govern how things are pronounced, and govern sounds. And because of that, sound of language determine emotional content of the entire culture. And you cannot just exchange it between, say, English and German. They sound differently, and people feel differently about things which they might even call, which they might understand in a similar way. And it turned out that in English language, differentiation goes much faster than synthesis comparatively to possibly all languages in the world. English is very good for differentiation. It is good for creating technology and science and to understand things. But it is pragmatic, but it is not good for understanding where I stand, what is my role in all of this thing. You can say things this way or that way, but what is my stand? English doesn't give you a clue. You really have to think on your own to do this kind of things. But if you go in other type of languages, such as Italian, for example, or Russian, which I know very well, or say Arabic, which is important today to understand what's going on in the world, synthesis is much more stronger than differentiation. Language is structured in such a way that in Arabic language, during the last 800 years, people virtually added not a single, maybe I'm wrong. I spoke to Arabic people, they told me that. I'm just repeating, I know nothing about Arabic language. Very few new words were added to Arabic language because of structure of Semitic languages. They are structured that way, and you can probably confirm to some extent or deny whichever is saying. They are structured in such a very difficult. Like in Israel, there is Academy of Science, which publishes in daily newspaper the last, whichever 3 or 7 words were added to Hebrew in the last day. Everybody have to learn it because these are new words that were added. One person cannot do it. It's very complicated. So there was no much, and so we know that of course planes are built in English language and well maybe in German and with stolen technology in Russian. But nobody builds plane with Arabic language. Just, people don't care. They just cannot. They care much more about the little knowledge that they have. They so much invest themselves in this knowledge. They don't need more knowledge. That's what they have is enough. So here are equations, which are related to those that I have shown you before, but not directly. It would be nice to relate them more closely. By the way, that's one of the directions where I would like you to get involved. So we can describe differentiation, say the number of knowledge, by how many words we have, or more generally, how many concepts we have in English. 10,000, 10 million, I don't know, 100 million. Synthesis is how much you value this particular piece of knowledge, your emotional attachment to a particular word. Actually, people measure this thing and they know it is different in different languages. But they didn't draw as much conclusion as I did. And of course, hierarchy is important because at the higher levels, models make sense of the lower level models. So these three, and it turned out that these three things which are measurable, You can measure the things from languages and from people. And you can describe, you can write differential equations. I don't probably have time to do this. So I'll just show you solutions of these equations. This is probably what was going on in Western culture for the last 2, 3, 4,000 years. Knowledge goes up and down. It is blue curve. And this red thing, which is emotional involvement in knowledge, is relatively small, also goes up and down. And of course, every up and down means a big war. Every down means a big war. Because if you lose 80% of knowledge, it doesn't happen just because you forget about it. It happens because of tremendous devastation, cultural devastations happen around, probably a war. And we are somewhere here. Are we on this side today, moving up? Or are we on this side today, moving down? And I'm now trying to get money to conduct these experiments and measure this.
Give me more money,
I'll tell you. And this is what I think is going on in traditional societies, and probably in Arabic society for the last several hundred years. So you see, emotional involvement in knowledge goes up and up and up. And it becomes so important that you cannot think about creating more knowledge. Knowledge is low as it's used, and almost doesn't grow. Stay wherever it was 800 years ago, that's probably is knowledge in many traditional societies, because it is impossible for them. Their language is built in such a way, so it is not like that they're stupid or lazy or don't want to think, or because they have bad politicians who want to control them, which is, of course, all of this is true. But all of this follows from the language. So maybe if we can kind of exchange these ideas around the world, so at least people will start thinking about it, maybe we can make a world a better place. Maybe people will start having more respect to each other. Maybe Arabic people will stop thinking that we are such a devil who want just to destroy their culture. And maybe we will stop thinking that there are such devils who try to destroy us. Even so, that's how it appears today. But so, and a lot of people are interested in military, a lot of people in government, a lot of people want to understand this kind of thing. It's clear we don't understand what's going on there. They don't understand what's going on here. So maybe mathematics will help us. Now, what happens if I add this term to the equation so that there are several cultures who exchange, and I'm sorry, I'm probably exceeds my time, but I'm about to finish. So if there are several cultures, traditional culture and this knowledge acquiring culture, and they exchange, differentiation and things, that's what happens. So first they interact and traditional culture get destroyed, but eventually you have two cultures that goes up, acquire more and more knowledge, but without much upheaval and downheaval, without much wars and destruction. Maybe this is Catholics and Protestants living together and exchanging, and a lot of other people living together in America and exchange their ideas. And maybe that's the reason how it works. Maybe multicultural societies, when finally people figure out how, instead of killing each other, how to talk to each other and live together, that's maybe how it should be. People in the world should get together, exchange ideas, trade, and maybe everything would be fine. Of course, some people say it's romantic, but well, who knows? Maybe that's how it should work. Okay, so that's it. So what is here is, if you want to continue thinking in this direction, so please do, and you can call me anytime you have an idea of how to do it, or at least first, of course, you complete your dissertation. When you become professor, you start thinking about when my son became, went into graduate school, the first guy who did for them orientation said, of course, you're all genius. But for the next several years, you do what your professor told you to do. When you become tenured professor, you'll start thinking. Before that, your professor think. So this is something to think after you become tenured professors. But keep that in mind. It will survive. These ideas will survive. They will be in the forefront of what's going on. If we want to understand mathematically how you get from dynamic logic to the entire hierarchy, so these equations will come up from the equations for recognition of objects. We don't know that. Psycholinguistic text. You really want, and that's I hope I will do in the next maybe half a year, really to measure in the lab the fact that there are differences, psycholinguistic differences among languages. And you can simulate this whole thing in mathematically with more details than I did and get different results and see what are the differences. And you can see which kind of conditions, environmental conditions will drive, which kind of languages and which kind of cultures. We need to understand the role of music. We know something. It is possible to understand the role of music. By the way, music is the greatest, mystery in history. Aristotle said that we don't understand why music affects our soul, and we don't understand it today. But we are getting close. If you get to web and get Perlovsky, my name, get to my website, you'll see there are ideas about music. So maybe we can improve human condition around the globe by developing this kind of model and trying to improve people's understanding of what's going on. And of course, we want to design semantic web and cyberspace where you walk into your home and your home understands what you need, and sensors are all over the place, and they read your mind and prepare your coffee and send signals to your friends at your home so that they can come visit you, whichever kind of is on your mind. So there is a lot of stuff that we can do for the next 100 years. So when you will be full professors, there still will be stuff to do from this list. And there was a lot of publications, of course. There is now about 280 publications on this topic. And there is a book published about 8 years ago. Now it is in sword printing by Oxford. And there is 2 other books published last year. And there will be another book published next year. And as I say, as you see, continuous number, papers are coming, 10 papers, 20 papers a year. So there is a lot of, no matter what is particular application you want to think about, you can probably find related papers. So that's what's going on. And you will have a copy of the thing, so you can look at it later. So thank you for your coming, and thank you for listening.
We have time for a couple questions. Yeah, Nathan?
I have a couple of questions on the cultural part. I mean, the study of culture is something great, unless it falls into stereotypes, and I couldn't help but feel that your analogy of the Arab mind as compared to the Western mind is similar to the science that used to be done 100 years ago, comparing the white mind versus the black mind and reaffirming one superiority over the other. I mean, you mentioned that Arabic is not fit for science. How could you explain that around the year 1500 it was the lingua franca of science, and algebra was discovered in Arabic? Now the part of English taking over does not mean that English is superior to Arabic. Maybe it's just the wheel of civilization, one civilization taking over another, and then.
Of course, what you say makes a lot of sense. And of course, I wouldn't go up with this kind of like crazy ideas unless I thought through answers to these questions. First of all, science is different from hearsays because science could be tested. Of course, all of you should know what's the difference between science and not science. Science is something that generates testable predictions and could be tested in the lab. And of course, I didn't have time to go through details, but there are, dozens of papers written on this topic, and there are specific predictions. And of course, in order to get money to start testing things in the lab, I came up with specific things that we want to test. So, and actually, they already had been tested for other cultures, not for Arabic, but for English and other cultures. And there are different emotional involvement. And there are very specific predictions. Those curves, they could be verified, and equations, they could be verified and tested and modified as needed. So the basic thing, again. Now, of course, people will come up, you're right, with all kinds of stupid prejudices, no matter what. You can have any kind of science, and people don't need any science to have stupid prejudices. The whole idea of science is to have something that stands against prejudice, because science can be verified. Prejudice cannot be verified because people don't care to verify it. So that's kind of like short answer to your question. Of course, what you say is absolutely right, and we have to make sure that what we say is, first of all, not inflammatory. And by the way, about 15,000 years ago, of course, what I don't know yet, because I don't have yet complete mathematical thing. I don't know how to explain what happens once in a while in every society when a new religion is born, when Christianity was born, when Judaism was born, 4,000 years, Christianity, 2,000 years, when Islam was born, how many, 1,200 years or 1,300 years ago. We don't know what happened at this point. People get tremendously excited. There are some ideas that somehow tremendously excite people's creative capabilities. And that was the reason for the first 400 years of flourishing of Islam, as well as it happens in every other religion. In Mayas and in Aztecs, there were this kind of periods. But then the language, and of course I don't have enough now scientific arguments to say, but because I just don't have time. I could go through the thing for 2 hours and probably you will be convinced, as I convinced my Arabic friends with who were our professors at Boston, somewhere where I found, and I talked to them, and they eventually agreed with me. This is what happens in many cultures, not necessarily in Arabic, in all traditional cultures that happen. Language is so emotional that it does not make people, look, we also are getting emotional sometimes beyond our ability to think. If your football team, favorite football team loses, some people go and crash cars around. They cannot stand it. They cannot think about how to make and nobody asks them how to make football team better. They just get too emotional. If your favorite political party, or God forbid your spouse, people does some strange things that you don't like, sometimes you say, look, get out. I don't have enough emotion to deal with this kind of situation. I cannot think about it rationally. There are situations where we cannot think rationally, even in English. Even so, the English is, as I said, the most, the least emotional word in language in the world. But by the way, of course, most of you here, as myself, we are not Englishmen. Some of us here are. But our emotionality is determined by mother tongue. Whichever we learned up to the age of 4 or 5 or 6, that's what determines to a significant extent our emotionality. And if you get emotional like I did, you see I continue to be emotional even if I speak in English. So it is not that just learning another language will cure you. It will help you. But by the way, as you have seen, it's very nice to have several languages inside of yourself. Then you can do both. You can acquire culture and not necessarily get to blows right away if somebody disagrees with you. And that was such a great thing of foreign people coming here and learning in English universities, maybe from foreign professors. But this whole thing, mixes cultures together and makes a possibility for advantage and makes hope that, well, maybe the world will become, even so today it's difficult to believe in it, but I believe that the world might become a better place maybe 100 years later, rather than just, having a Holocaust, atom Holocaust around and nothing will survive. So I hope it's possible.
Any other questions?
I had to comment on 2 questions. Comment would be, it was interesting, your point about the hierarchy of models. And so what this would point out is those guys over there in Europe on the France-Sweden border, the Large Hadron Collider, this is just their quest for God when they're going to fire that guy up in a couple months, get the Higgs boson, and finally they can get their model of everything, get their quantum gravity. So there you go, that's their religion. One thing would be talking about filling in the blanks. If you start with an infant and as you age, this is what you do. You take your models and fill in the blanks. So you just start out with a worksheet with a little bit of information and a lot of blanks, and you fill it in. It's curious, from the standpoint of the neurons, what's going on. You've got the 100 billion neurons, and you've got the estimated 1,000 trillion connections, and if you do the math, it's 10,000 connections per neuron. But as far as language goes, you have your primed period that you mentioned, I guess stage 4, language acquisition device is really on the prowl. It's phenomenal what you can do. But in the brain, you're starting out and you're actually, you would think, you think about the synapses, and new synapses means new information or new ways of dealing with things, but it's actually the opposite. It's actually a subtractive process. You go from 1,000 trillion to, by the time you're an adult, 500 trillion, to some people would say a factor of 10. So
Yeah.
there's a lot of debate about that kind of stuff. So, and that is related to these filling in the blanks. And actually, a lot of people point out that this is somewhat a hardwired phenomenon. These are things that, you know, if you pick up the flute a lot and you build, this is kind of a background paradigm that you then apply to a lot of other situations. So do a lot of reading, you build in these, and then there's also the question of the plasticity. And this directly contradicts that, where you have 50-year-old men who have their stroke and lose the ability to read, and then the brain completely reroutes around it, and they relearn. In fact, that happened to my grandfather. He had 2 massive strokes, and you know, that's what he does all day long, is read, and lost the ability to read, difficulty speaking, and brain rewired itself, and a couple months later, he, you know, sharp man. So I was curious about your models, and you know, if you have any insight into these things and how it all works.
Okay. Yeah, of course, if you call it one question, okay, let me take it by parts. The first question was about Higgs boson and God.
Oh, wow.
And yeah, some people really think that they will have answers to everything, and I used to be a physicist, high energy physicist, theoretician, and thought that this is very important. And for these people, indeed, finding this final kind of like piece in the unified theory of matter would serve as, for many of us, God. But of course, the ultimate thing is that God is related, I think, and not just think, I can explain it, and I wrote a paper on this, but it will take a long time to explain. God is related to this top model of the meaning of all the knowledge that we have, and the way how we feel about it, that it is a model of our meaning of life. And God is related to this thing, but it will take a few more logical steps to explain how God is related to this thing. Yeah, for some people, God is associated with traditional religion. For other people, for physicists, God is associated with understanding of the meaning in the universe. So these are related things. They're not really completely different. But of course, it is not that Higgs boson is God. It's by itself. The God is related to the fact that people feel that there is meaning and purpose in the universe. And some people, namely physicists, associated with physical theory, and that indeed is tremendously inspiring. But of course, it is not like the finding boson will find your God. You will still, you know, life wouldn't stop at this point. Hopefully, we will exist for a while. And the next your question was about neurons and how is it possible that people can rewire, so to speak, their wiring even after 50 years old. Well, we don't really know about it. We only know that part of the thing is fixed from the birth. Other things are fixed in our brain in such a way that neurons are remaining rewirable. Unfortunately, we cannot grow another limb. If we lose our hand, we will not be able to, you know, grow another one. But neurons in the brain maintain significant part of their flexibility and you know, being adjustable and reroutable and whichever, being adaptable. And yeah, we are happy when it happens, and certain things could be, and it depends very much on how much people want to achieve this, because these neurons, well, we know how they work in principle. If people sense their signals, they continue grow and continue rewiring. And I know a girl who was professor at Yale, and then get in tremendously bad accident. And people say she will never read, never walk, never drive, never understand anything. And indeed, for half a year, she was barely just sitting in her chair after she was really, you know, rewired just physically. But I have seen her recently, 2 years later. She is going, working and talking, and she is already much more than half a person. She is almost a full person. Not quite yet, but maybe another few years. So there is tremendous ability to rewire our brain, and I believe it's to a significant extent, not maybe to 100%, significantly depends on how much we want the thing to happen.
Yeah. Also, interestingly enough, in this week's Nature, there was a guy, Bart Selman from Cornell, Ithaca, and he was talking about taking techniques derived from statistical physics, modeling ensembles of atoms, and applying it to some of these categorization problems, like you were saying, some of these MP complete. The example that they used was the hitting problem, which is where I think it was you have a group of students, you take them and you say, you know, Bobby plays soccer and football, and maybe they threw in music, plays the flute, and you try to group them, at least for this particular problem, is grouping the fewest number of students that contained everything. And so they applied these methods to at least that MP complete problem, as well as others, and got good results. I don't know if that would be applicable to your particular problem or not. You probably have to look at the more specific details, but that's the general gist of at least one kind of grouping that they were doing. So I don't know if that would apply going from pixel to object, to whatever, this problem. But they did mention, the DARPA Urban Challenge being one application, which would imply that this would be right up your alley that they were talking about.
I can say the following thing. People try to do this physical mechanism, apply them to mind for a while, from time to time, and it didn't work. I think there is, of course, you can set up a situation where it works, because physics is powerful. But I can give you a very fundamental reason why it wouldn't work in general. The reason is as follows. Statistical physics is governed by entropy. That is, everything will become more and more random. Concepts cannot appear. If you have concepts at the beginning of the system, as a result of thermodynamic equilibration, they will disappear. Knowledge instinct is, that I was talking about, is a different, entirely different kind of very high-level organization of the thing, where things are becoming more and more complicated, where entropy within a confined system goes down, not up. Emotion goes up, information goes up. Whereas in entropy, in entropical systems, such as statistical physics describe, information goes down. So it will never, you will never be able to use statistical physics to describe what goes on in our mind. Even so, it's amazing that, of course, every individual little piece of neuron, of course, is described by statistics. Well, but who knows where and how? If you set experiment in the proper way, you might show that entropy is there, but it will never be able really to describe how the mind works.
So let's give a chance to somebody else. Yeah. One last question. Yeah.
Yes, to bring this slightly back more to computing, how exactly were you modeling the emotions and the hierarchy that you described in your computational models?
Okay. Yeah, emotions, there is nothing, some people think emotions are mysterious. Nothing is mysterious about emotions. Emotions are much simpler than concepts, because they appear much earlier in evolution, and they're a very simple mechanism. And by the way, emotions are not what people use for communication. Sometimes people use emotions for communications. That's not kind of emotions that I was talking about, even though they're related. The emotions that I was talking about are specific emotions related to learning. When you get more knowledge, you are happy about it. And it is inborn. Everybody, to different extent, are such organized. So emotions, they naturally appear when your instinct is satisfied. That is emotional, kind of emotional process in your brain. It is not that emotional signals in computers have different color on them and words saying emotions. In computers it's just saying. But of course, if you are talking about a single computer or a few lines of code saying this is emotional signal, you'll doubt. You wouldn't believe in what I say. But if you have, say, 20,000 of robots with this kind of brain, communicating among each other and having emotions about different parts of knowledge that they have, then maybe we will get more kind of used to really accepting that as emotion similar to our emotions, rather than just just an electronic system. Why call it emotion? So, but of course, in your brain there are all kind of electronic signals, and some of them we perceive as emotions, some of them as not. But our perception is kind of secondary to what brain, even so related, but secondary from what actually brain is doing. So there are emotions, but they're no different from any other signals in terms of their physical appearance. There are emotional signals because some people say, and that was not my idea, that emotional signals are connecting decision-making with instinctual part of the brain. So if this certain decision will satisfy certain instincts, you perceive it as positive emotion. If certain thing does not correspond or violate your instinctual need, you will perceive it as negative emotion. But the electrical nature of electrical signal, of course, doesn't change.